My name is Maugan de Murcia. I'm a PhD student at the Exlim Institute of Poitiers in France. And I'm here to present you my research work, which is related to software-defined radio and optical communication. So today, with the current development of new technologies, such as the Internet of Things or the cloud computing, we are observing a massive increase of the data traffic at a global scale, which is therefore pushing the radio frequency-based wireless network to their limit because of the spectrum boundaries. So now the solution broad consists in extending the use of the radio frequency spectrum with some unused bands, just like with the fifth or sixth generation. But it seems that this solution will not be enough to answer the future data needs. So this is why the optical wireless communication appears like a promising complementary solution to radio frequency-based systems, because instead of using the radio frequency spectrum, it is using the optical spectrum. And in my case, I'm especially working on visible light communication. As the name suggested, it is only restricted to the use of the visible part of the optical spectrum to communicate. So in order to facilitate the development of VSD system, the concept of software-defined radio, which provide a great flexibility in the implementation of radio frequency systems, is as well applied to VRC system, which is therefore given rise to a new concept, the software-defined VRC. So just to talk a little bit about my thesis context, we are working as part of a research project with a lighting manufacturer company, because they wanted to add some smart lighting solution within their own products, which is mainly intended for the professional and industrial environment. So here there's an example they already developed, which is a table lamp that was used in restaurants to transmit the restaurant menu through the light variation of the light. So the customer just had to use their phone to receive the menu. And they developed this application in response to the sanitary constraint imposed by the pandemic. So the objective for my thesis is to implement and design a software-defined VSC testbed in order to be able to test different kind of VSC systems, and also to develop a VSC library that will be open source and shared to the community. So my presentation is divided into 4 main sections. First, an introduction to optical wireless communication, followed by an introduction of software-defined VSC. I will then present you our implemented testbed and how we validate its operation. And then I will just conclude and give you some perspectives. So the optical wireless communication refers to the transmission of an information based on the free space propagation of the light from the infrared to the ultraviolet light. So the objective of optical wireless communication is not to completely replace a radio frequency system, but rather to bring a complementary solution, because both technologies doesn't have the same advantages and drawbacks. So compared to radio frequency system, EuGRD get some advantages like higher and non-regulated bandwidth, a higher free security because light cannot pass through the walls, so your information gets stay within the room. You also have no electromagnetic interferences and lower implementation cost. You also have some drawbacks, like communication blockage, especially if you have an obstacle between the emitter and the receiver. The ambient light noise, which can be due to the sunlight or the indoor light, for example, and also limited power because of some health regulations. So since the application range of optical wireless communication is very large, from a simple TV remote control to inter-satellite communication, OWC can be classified into different subsections according to the different specification of each system, just like the transmitter, receiver, or propagation media. So you have, for example, the free space optics, which is particularly suited for the long-range P2P communication. It is based on the laser diode at the transmitter and a photodiode at the receiver, and you can use all the optical spectrum to communicate. The Li-Fi, light fidelity, which is the equivalent of the Wi-Fi but using light waves, which uses both LEDs and laser diode as transmitter and photodiode as receiver. And you can see that the particularity is that for the downlink, you only use visible lights, so you can also do some illumination. And for the uplink, you can use all the optical spectrum, but mostly infrared, so you can avoid some interferences. Visible light communication, the one I'm working on it, which is using the same transmitters as the Li-Fi, but you have also a different kind of receivers, just like a camera and a solar cell, for example. And also the optical camera communication, which is here only based on the use of a camera at the receiver to communicate. So since here at the output you don't have a signal but a picture, you can use different kind of transmitters, such as a display or QR code, for example. So the visible light communication, the main purpose is to do both illumination and communication at the same time. So these systems are mainly based on the use of a LED at the transmitter and a photodiode at the receiver, as is shown here. So since you want to do both illumination and communication, the transmitted signal needs to have both a DC and AC component to do both illumination and communication. Yeah, since the light transmitted by the LED is non-coherent, meaning that you cannot use and predict the phase, most of the VSC systems are based on the intensity modulation direct detection scheme, which refers to the transmission of an information based using the brightness variation of the light emitted by your LED. So this principle is imposing two main conditions on your emitting signal that will be both positive, because you can't have negative intensities for the LED, and also real, because you can use phase modulation. Yeah, since one of your objective of the VSC is to do illumination, you need the communication to be completely invisible for the human eye, so you need the frequency of your signal to be higher than the critical frequency, over 100 Hz, in order to avoid some flickering effects. Now about the software-defined VSC. So since the SDR was initially developed for the needs of wider frequency transmission, it is not totally suited for the VSC transmission because of the difference of both technologies. So if you want to use SDR to perform VSC testbed transmission, you need to first make some adaptation. The first one is that you need to use baseband transmission because you want to do illumination, so you need to have a DC component. And the second one is, of course, you need to replace your antennas by optical front ends in order to as is shown on the diagram here, you want your signal to be only positive, so the objective of the driver is to put an offset so that you only have a positive signal to feed the LED. So here is a scheme of the basic architecture of a SDVSC testbed. So just quickly, you have, of course, the software part, which is sending the signal to your hardware, which is then transmitting the signal, which is bipolar. You have your driver that is giving an offset to your signal, here in red, and also converting the voltage in blue into a current to feed the LED. The signal is sent to the photodiode, which is then generating a photocurrent in red IPD, which is converting into a signal voltage digitalized and sent to your software in order to be processed. So now about the testbed. So like the great majority of SDVSC testbed, we are using USRPi because we can easily enable the baseband transmission using some dollar worker. About the emission, we developed a special optical front end with a 10 MHz bandwidth, which is actually pretty simple, which is just composed of an amplifier, a MOSFET, and of course some LEDs. And at the reception, we are using the PDA3682 photodetector from Tom Lyles, which is actually composed of a pin photodiode and a transimpedance amplifier. And since we want our testbed to be very flexible in terms of modulation schemes, but also configuration, we developed a mobile trolley so that we can easily change the communication distance, but not only, or we can also change the height of our photo detector and also the orientation, so that we can not only do some line of sight transmission. So regarding the software part, we are of course using GNU Radio and the GRWC out-of-tree module that was developed and released by academics for the needs of optical channel propagation modulation within GNU Radio. So this out-of-tree module is implementing different kind of modulation schemes for accuracy. So this is why we use this library to make our testbed. So here is the basic photograph for an OK transmission using this library. But the main issue that we face with this library is that since it is developed for simulation needs, the developer didn't take into account the synchronization of the receiver, because since we are simulating, your emitter, transmitter and receiver are basically synchronized. So if we want to use this in hardware implementation, we need to provide some more synchronization. So if you want to synchronize a digital signal, a very efficient way is to use a phase lock loop structure, as is shown here. And actually, if you want to if you want to determine the optimal sampling instant of your signal, a better way to use it is to use the eye diagram representation as it shows here. Since the optimal sampling instant corresponds to the maximum eye opening, so here on the scheme, your signal is digitalized by the ADC, then pass through the match filter in order to determine different symbols. Then it gets to the interpolator, which will then adjust the alignment of your samples with the maximum eye opening in order to provide the synchronization. And the phase lock loop is composed of a time error detector, which actually computes a phase error signal according to the interpolation control and the signal clock at the output of the match filter. Then this error signal is filtered by the loop filter and then gets to the interpolation control. And this one is using this error signal in order to correct the clock of the interpolator to provide the synchronization of your incoming samples. So to do this in GNU Radio, we are first using an EGC block in order to maintain a constant level amplitude for the synchronization. Then we are also using a asymmetric field filter, which is here acting like a match filter, and the famous symbol sign block, which implement different time error detector algorithm. And this block is basically acting like the previous clock recovery and polyphase clock sync block. And as it was already said, Hervé will talk about this block during this afternoon. So if you have any question, keep them for this afternoon. So here is the reception photograph of our OK transmission. So you see here in red that we add some synchronization in order to correctly receive our signal, and then we just demodulate our signal and record the generated signal into a file to be then post-processed. So about the validation of our testbed, the idea to validate the operation was to use the bit rate measurements, since the bit rate measurement refers to the number of transmission errors. So if our transmission errors are only due to the propagation of your signal within the channel, it means that you are synchronized, and so it means that the synchronization is working well. So to do the bit rate measurements, we measured the transmission error for different SNR values. So in order to measure the SNR, we first wanted to measure the power of our signals using a spectrum analyzer, but since we are using baseband transmission, our signal and spectrum analyzer was not able to measure correctly the power of our signal, so we use instead an oscilloscope and determine the SNR with the 1 mean squared values. The The main issue we faced during those experiments is that to have valid results, we need to have full control of the environment. And since the photodetector has a great sensitivity, a simple variation in of the ambient light has a great impact on the SNR value. So in order to make valid experiment, we perform our measurement in complete darkness. And to have different SNR values, we just simply change the communication distance between the transmitter and the receiver. So about the leader rate, as I already said, the demodulated signal is recalled within a file. So we just then compare the received signal with the original one in order to detect the transmission errors. And to have a valid beta rate, statistically speaking, we took at least 10 transmission errors. So usually beta rate curves are plotted not as a function of the SNR, but the EV over N0, which corresponds to the energy per bit over the noise power spectral density, which corresponds to the normalized SNR without taking account the bandwidth. And in order to compare those results, we use the expected error probability of the OK transmission, as it is shown here, in order to have a reference for our measurement. So here is the result of our experiments. So you see in red the expected probability error, and in different color the three different TED algorithms that we experiment: the maximum likelihood, Maugan, and zero crossing. And the first thing that we can see is that the zero crossing is the one that got the best effective performances, but still it is pretty close to the theoretical expected value with a difference less than 1 dB. And the maximum likelihood and Maugan algorithm got the best performances and very accurate, especially with beta rates less than 10 to the -3. So to conclude, during this work we design and implement a SDVSC testbed based on GNU Radio, and we validate its operation through the measurement of beta rate, and this for different kind of TED algorithm. And to give you some perspectives, we like now to validate the operation of the testbed for non-linear cell transmission using the reflection of the light within the environment, and also we want to integrate the different VSC receivers, so the camera and the solar cell, in order to have a big complete SDVSC testbed, and so we could experiment different VSC systems. So thank you for your attention, and if you have any question, I'd be glad to answer them.
What's just out of interest? I didn't get what the symbol rate is that you're working with. The symbol rate, I just forgot. What's the baud rate?
Symbol rate? 100. Oh yeah, 100 kilohertz.
Okay, that's pretty fast. So how do you set the threshold for the OK? So when is it a 0? When is it a 1? How is that determined?
Moving average block.
And
computing.
Is that mathematically optimal? Because I remember, like, this is my undergrad. This might be a bit in the past. That if you have OK, then your detection, the optimal detection threshold for a 0 is not just in the middle or somewhere, but it's like depends on the absolute relation.